Hey everybody, this is Alex Merced, and welcome to the first ever Lakehouse Lunch. This is a series being put on by the Data Lakehouse Hub, which I'll talk more about in just a moment. But this week we're going to be doing a topic that I'll be presenting on. That is a primer on Apache Arrow and Apache Iceberg. Okay, and again, my name is Alex. I'm a senior tech evangelist for Dremio. Now, let me just tell you a little bit about the Data Lakehouse Hub. Data Lakehouse Hub is an online community for people who are interested in the Data Lakehouse space. By scanning this QR code, you can join the Data Lakehouse Hub Slack community, where you can find me and many others. So feel free to message me there as well. I do travel a lot, so in many cities within the U.S. So over there at the Data Lakehouse Hub Slack community, I have different Slack channels created for many of the cities that I travel to often. So a great place where you can network people in your local area. And also, if you have events that you're organizing in those areas, feel free to post them there and find out events that I'll be speaking at. And again, the Data Lakehouse Hub also is available at the datalakehousehub.com. You can also join the meetup group where this event and many other future events will be listed. So you can scan that QR code there, and that'll take you to the North American Open Data Lakehouse Link Up meetup group, which is organized by the Data Lakehouse Hub. And we'll get you so that way you never miss an event. And I'll also tell you about other events outside of the events organized by the Data Lakehouse Hub regarding the Data Lakehouse. And if you're interested in speaking at a future Data Lakehouse Hub, Data Lakehouse Lunch, you can just send an email to this address, speaker at Data Lakehouse Hub. Please just send some details about sort of like what you would like to speak on. Ideally, it would be about the open data lakehouse and technologies like Apache Iceberg, Dremio, Nessie, Apache Arrow, and so forth. And just sort of like implementation, architecture of a data lakehouse, and so forth. So just send those details there and we can get that scheduled. But with no further ado, let's get on to the presentation today, which is myself with a primer on Apache Arrow and Apache Iceberg. Okay, now let me tell you a little bit about myself. My name is Alex Merced. I am a senior tech evangelist for a company named Dremio, which I'll tell you more about in just a moment. But I've worked in the web and data spaces, writing code, helping people figure out their data modeling, all sorts of really fun things. And now basically I spend my days advocating and evangelizing the Data Lakehouse, recently co-authoring Apache Iceberg, the definitive guide for O'Reilly. But I also speak at a lot of events like Data Day Texas, Data Council, are all events that I've spoken at in the past. I also host several podcasts. But as I mentioned, I'm a co-author of Apache Iceberg, the definitive guide, which you can download a free copy of by scanning this QR code here. So again, whether you're watching this live when we have this event live, or you watch this when we post it on YouTube afterwards, you'll be able to scan this QR code to download Apache Iceberg, the definitive guide. Okay. Also, I am currently doing an ongoing Apache Iceberg crash course, which you can register for, by going to this link right here. Okay. And this QR code right here. Again, we're about 6 sessions in, so there's 4 sessions left. But you can watch all the previous sessions on demand. So all you have to do is register there. Here are the podcasts that I am a host of: Gnarly Dataways, Data Nation. All of these can be found on iTunes and Spotify to, well, learn more. And as I mentioned, I'm from a company called Dremio. And just a little quick bit on what Dremio is. Dremio is the unified lakehouse platform for self-service analytics and AI. Now, what does that mean? Bottom line is that Dremio helps you get more value out of your data lake or your data lake house. And it does it sort of in 3 categories of value that it provides you. It does through unified analytics by letting you connect all your data sources, whether they be databases, data warehouses, or data lakes, into one place where you can work with all that data from one place, where you can govern that data from one place, model that data in Dremio's semantic layer, all from one place, to deliver those business metrics and business data sets that you need for your business users. But along that, Dremio has a very powerful, very fast SQL query engine that allows you to federate queries across all those different sources, so that way you can deliver data fast to those business users with very powerful acceleration technologies, particularly reflections, which basically not only improves performance, but can also really reduce your costs when querying your data lakehouse. And the last piece is through lakehouse management. So if you are doing an Iceberg data lakehouse, one of the challenges with the data lakehouse is that you have to manage those tables yourself. Unlike a data warehouse or a database where a lot of the data optimization kind of happens behind the scenes, in a data lakehouse, well, that's done in the open. That's done by you. But you can have a tool like Dremio that through its enterprise Iceberg catalog can not only track your tables but also make sure that they're always in good shape by auto optimizing them for you, doing a lot of the cleanup work for you, also providing you a catalog that has Git like versioning where you can isolate workloads on your data, create zero copy clone environments, and a lot of other really cool benefits when using Dremio's enterprise Iceberg catalog is part of its Lakehouse management features. So through unifying your data, through its SQL query engine, and through Dremio's Lakehouse management features, Dremio provides a lot of value to working with your data lake and data lakehouse. And you get all of that in any environment you want. You can deploy it in the cloud, you can deploy it on-prem, you can connect the data sources on-prem or in the cloud, and unify all that data in one place. So if you ever wanted to join a Snowflake table with a table that you have in a Hadoop data lake, well, you can do that with Dremio. It gives you that kind of hybrid flexibility for the modern hybrid data lakehouse. Now that we got that out of the way, we can begin with our feature presentation. And again, we're going to be talking about specifically about Apache Arrow and Apache Iceberg. Okay? But both of these technologies are going to be really vital to a specific trend, a specific architectural pattern that is the data lakehouse. So let's learn a little bit more about what a data lakehouse is first before we get into Apache Arrow and Apache Iceberg. Okay? Now, first off, when we think about traditional data systems, okay, they generally fall into one of sort of two categories typically: databases and data warehouses. Databases typically for like transactional workloads where you're, adding a row, looking up a row, you're doing much more row-based transactions. Well, data warehouses where you're doing more analytical transactions, but they both essentially do the same things for you. Okay, they're gonna abstract away how you store the data. So when I create a table in Postgres, the data is stored in the system. How it does it, I don't know. What format and how does it keep track of it, I don't know. And how does it know which data is table A versus table B, aka table format? That's also abstracted away. So all these things that system, that sort of integrated system is doing for me. A catalog. How does a database and a data warehouse know or is aware of all the different tables that are in the system? Table A, table B, table C, table D. Well, that's because also part of the abstraction is a catalog that tracks all the different tables that are part of the system. And how does it work that I can write an SQL query, that SQL gets parsed, turned into an execution plan, and then that plan gets executed, giving me back the results that I want? Well, all this is generally part of the bundle, the software system that is the database or data warehouse. It's all integrated. Oftentimes when we're talking about databases, we're working with row-based data for transactional purposes. When with data warehouses, we're often working with columnar-based data for analytical purposes. But at the end of the day, all these sort of layers of work are abstracted away. And that's all really well and good. And that's why we like databases and data warehouses. They're easy to work with because they make it where we don't have to know about all these internals. But the catch is each system does it their own way. Each system stores the data their own way and does each of these things their own way, which means that the data in one system is not necessarily usable in another system. And this becomes a real challenge when it comes to analytics because oftentimes we need many tools for analytics because there's so many different ways we want to analyze the data, so many different use cases, so many end goals, whether we're talking about AI, ML, BI dashboards, reporting, creating data applications. There's all sorts of different ways we can use the data, and usually one tool won't necessarily fit every possible use case. So in this case, we end up moving that data across many different systems. So we end up with many copies of the data for each system, since each system is kind of its own black box. So in this kind of world where we need to not only deliver data faster, but cheaper, because again, it costs a lot of money to move the data into all these systems. It takes a lot of time to move data into all these different systems. It'd be nice if I only have to move the data once. That's going to save me in storage costs, save me in compute costs from all that reduced ETL, and so forth. But the question is, what kind of system will allow me to do that? Only if there was somewhere where all my data was stored that anyone can access. Well, we do have a system like that. It's called a data lake. And essentially all a data lake is a distributed storage system. So it could be like a Hadoop storage system, an object storage system like an S3, an ADLS, or MinIO. But the idea is that it's a storage system where I can store files, which can include my structured data, and generally in the format of like CSV, Parquet files, or unstructured data like MP3, text files, whatnot. I can put all that data and just store it here. And generally, I could run queries and do workloads off this data using tools like Dremio or AWS Athena to run SQL queries against this data in my data lake. The problem is that at the end of the day, they're files. Okay, they're not tables. So I might have a really big table. Okay, so that might take up like 1,000 Parquet files, and systems just won't inherently know that those 1,000 Parquet files are one data set, which means different tools might end up inconsistently querying that data. On top of it, you don't have the same sort of guarantees as you do in database and data warehouse systems. There's just a lot of things lacking. And as you can see, the reason is because we're missing some of the pieces that are part of those larger integrated systems. So how do we fix that? Well, we put those pieces back in. Okay, we take that storage layer, we can take the existing tools we have to run queries against our data lake, but then we add in a table format like an Apache Iceberg. We add in a catalog like, let's say, a Nessie or a Polaris. And now you have that whole story back again. And you now have those same kind of guarantees as a database or a data warehouse. The ability to consistently define data sets, the ability to query them very, very fast because the metadata acts as an index. You get all that, you basically end up building a data warehouse. It's just now using your data lake, thus the term data lake house. Okay? That's all it is. All a data lake house is just saying, hey, let's build a data warehouse like system where our storage layer is our data lake. And then we just build those abstractions on top of that. But there's a couple of technologies that really make this practical, because at the end of the day, there's a couple different things. When you need this table format and you need this compute engine to be fast enough to run queries, so that way it is just as fast as working in the data warehouse. Okay? And there's two technologies that we're going to talk about that kind of really, really help with that. So first we'll talk about Apache Arrow. So Apache Arrow, not only used in data lakehouses, but in anywhere you need to process data. But essentially the idea is, the problem was this. Generally, traditional database systems were all row-based. So I mentioned that they're row-based, which is all fine and good. But that's not the fastest way to represent data for analytical type workloads. So typically analytical systems would represent the data as columns. So that way you can just grab the columns you need. But every database did it differently, or every data warehouse would represent that data in memory differently. So the problem is, when you would have two problems. One, when you send the data between different systems, it takes longer because even if they both speak columnar, they would have to convert between different columnar formats. Okay, when you send data from one system to the next. And typically when you send data from one system to the next, you would use like JDBC, ODBC. And you'll see later on that JDBC, ODBC generally sends data over as rows. So you'd have to constantly be doing all this conversion. And there's a cost to performance when you're constantly having to serialize and deserialize data, convert data from one format to another. How do you avoid converting? If everybody uses the same format, you don't have to convert as much. So Apache Arrow, one of the things it's trying to do is create a way of representing data in memory. So this is not a file format. Generally, you'll represent the data. The best way to represent the data as a file would be like Parquet. Instead, but what happens when you load that Parquet file to actually run queries against? How do you want to represent it in memory while the program's running? That's where Arrow plays. So it's an in-memory columnar format. The idea is when you're processing the data, how is the data stored in the computer's RAM or memory during processing time? So basically, the idea is one, to create one that's really fast, and in a really fast format that's columnar, but also to do it in a way that's an open standard, so that way you reduce those deserialization bottlenecks when you have multiple systems working together. And this format, Apache Arrow, is actually partially co-created out of Dremio. One of the co-creators of Apache Arrow is one of the founders of Dremio. Okay. And again, the reason being is that the purpose of this is to speed up processing of data. Okay, while you have Apache Parquet, that solves a different problem on how to store the data to storage. So when we think those are two different problems, so they require two different solutions. How do I process the data faster versus how do I store the data for fast retrieval for analytical workloads? That's the problem that Apache Parquet solves. Now, so again, it's an in-memory format. Now, of course, you don't want everyone having to manually have to create these Apache Arrow type objects or when they write a program in any language. So part of the Apache Arrow project is actually creating the libraries in every language, so that way whatever language you're writing your program in, you have the ability to take advantage of Apache Arrow. So there's Apache Arrow libraries in pretty much most of the modern languages: Go, Rust, Java, C, C++, JavaScript, Python. And these libraries will allow you to write data to Apache Arrow tables and buffers, allow you to read and retrieve data and convert from other formats into Apache Arrow, so that way you can work with Apache Arrow and do a lot of the computation in Apache Arrow, because again, Apache Arrow is going to be really fast. It's really designed to be really, really fast. So it's designed to be fast, but it's also designed to be standard. And when you have both of those, you end up giving a lot of performance. And again, as I mentioned, that one of the co-creators of Apache Arrow is one of the founders of Dremio. That's why Dremio has been built using Apache Arrow for processing pretty much since its like inception, which is one of the reasons why Dremio is as fast as it is, and why you're going to see other tools that I'll mention later on that are now leveraging Arrow, and you're starting to see this huge ecosystem of tools leveraging Arrow, giving you really fast performance. Okay, so again, you have support for many languages. It was co-created by Dremio and Wes McKinney. And Wes McKinney, probably famous for being the creator of Pandas. So he's also a co-creator of Apache Arrow. It was super popular. I mean, right now it's becoming really the standard for how you do all data processing. Most tools are using it. So you can see here, like, it had a huge astronomical growth as it caught on. But the thing is that one thing is, how do you process the data? But the thing is that you still have to send data between multiple computers, right? So not only, so that's a different bottleneck. So how does one computer hold the data in memory to process that data as fast as possible? It's one problem. Second problem is, how do I transfer that data for ultimate performance? So basically they address the second problem with a sub-project of Apache Arrow called Apache Arrow Flight. So Apache Arrow Flight is essentially, think of it as like a modern answer to JDBC ODBC. The idea is, like, how can we transfer data over in a columnar format? Okay, well, JDBC ODBC, I could send data between systems using JDBC ODBC. That data has to first, if it starts from an analytical like data warehouse, it's going to start out columnar, have to be turned into rows, sent via JDBC, and then converted back into columns. Okay, and that's going to take time. So Arrowflight is a gRPC framework, which is a way of building a standard API for sending over Arrow data in that Arrow format from one computer to another, so that way you don't have to convert. Okay, the idea is that if it starts as Arrow, because you're using one Arrow system, and then you send it to another system that uses Arrow, and you use Arrowflight, the data never has to convert. So that means you save all that time. Okay, and I do have like a video on YouTube where I compare using JDBC to Arrowflight, and you can see the difference when you start getting into lots and lots of rows. So the more records you're sending over, the bigger the benefit here is, because every additional row you have to convert back into a column means more time it takes to get to the actual processing. So basically, Arrowflight allows you to send data over in a more columnar format, and also the way that the Arrowflight format works, it's not just, hey, send data from point A to point B. It actually works through a ticketing system. So what you do is you would send a request saying, hey, I want to get the results of this query, and then generally what can happen is that you might get tickets for example, you could split that work across multiple computers, parallel processing, and then generally each of those tickets, you'll get like essentially it's a token, but it's called a ticket that represents, hey, here is the thing that will let you retrieve the data from this machine directly for that chunk of the response. So this will allow you to split the work up among multiple machines and then go retrieve the data from those multiple machines directly to give you sort of parallel retrieval. So the idea, again, to help maximize performance in systems. So again, these are things that it enables. Doesn't mean every system that uses Arrow takes advantage of all these features, but the idea is designed to kind of have that flexibility, so that way you can really maximize performance if you take advantage of its full-on architecture. And again, here's a good example of what I was talking about earlier. So when you're talking about a few amount of records, like 2,000 records, you're not going to notice that much of a difference between using ODBC versus Flight. But when you start doing a lot of records, again, all those conversions start getting expensive. So you can see here with Flight, no, I don't have to convert anything at any time. So I get that data transferred over from wherever I'm requesting that data to my laptop much, much, much faster. Okay, and it makes a huge difference, especially when you think about like training AI models and you want to pull large amounts of data. All these things are going to affect like the performance at the end of the day. Okay, now the problem with Apache Aero Flight is that gRPC can be a little tricky for a lot of people. So they make it easier and also make it allow you to write SQL against those Aeroflight in that Aeroflight framework. They created Aeroflight SQL, which is just basically adding to that Aeroflight protocol the ability to kind of send SQL statements. So you can send SQL statements to any Aeroflight supporting tool like Dremio. So the idea is like the same protocol you use to communicate to Dremio, you can use to communicate to lots of other tools like Influx Data that support Aeroflight. Okay, which is really cool. Because before, like if you ever use JDBC, ODBC, you've probably noticed you have to download like different drivers for different systems. You have to configure those drivers and all that stuff. Not a lot of fun. So the idea is having a standard format where everybody kind of follows the same exact rules and you don't have to download multiple drivers all the time. That's pretty nice. Okay. So again, bottom line is Aeroflight as SQL just kind of adds on to Aeroflight to make it where you can send SQL over to an Aeroflight system. Okay. And again, always the thing is not only do you want to make something that helps, but you want to make it easy to use the thing that helps. So in the journey of making using Aeroflight SQL easier, okay, because what people are used to doing, they're used to using ODBC and JDBC. So actually, Dremio created ODBC and JDBC drivers that actually even they can basically they look like ODBC and work like ODBC JDBC drivers, but they're actually using Aeroflight, allowing you to connect to any Aeroflight supporting endpoint. So those exist. They're now part of the Aero project, and they allow you to connect to Aeroflight sources using ODBC or JDBC. And then on top of that, the Aero project created a whole new protocol called ADBC, Aero Database Connectivity. Okay, and again, for those unfamiliar with these acronyms, it's Open Database Connectivity, Java Database Connectivity. Now it's Aero Database Connectivity. This new protocol, ADBC, will basically is a columnar protocol. The cool thing about ADBC is that it doesn't have to be Aeroflight. So for example, if you want to connect to another data warehouse that has a columnar format, but let's say it's not using Aero, they could write an ADBC driver, and now you can communicate with them in a columnar format using their particular driver. So there's an Aeroflight driver for ADBC that allows you to connect to anything that has Aeroflight. Again, think Dremio, InfluxDB, and others. But then there's also other people can create their own ADBC drivers for their own specific columnar implementations, creating sort of a standard columnar-based protocol in the same way that ODBC, JDBC are really a standard row-based protocol. Okay, and all of this is completely open source. And another really cool thing that's happening, so you have companies like Dremio, again, has been using Apache Aero pretty much from the beginning, and you have a couple other really cool projects. So you have like Data Fusion. Data Fusion, which I think was originally called Ballista, is a query engine that was built. That's based in open source. Think of it as like a Apache Aero-based DuckDB in the sense that it's a query engine that you can just load up on one machine or work across many machines. You can use it as a Python library in the same way you can use like DuckDB as a Python library. That's written in Rust and gaining a lot of popularity for, hey, if I just need a quick query engine to run some queries right from my laptop, I can just spin up Data Fusion and work with really large data sets right from my laptop. Okay, well, again, Dremio is more like, hey, we have really, really large data sets that I need to share with people all over the world. So you create a Dremio cluster and you can share within your whole company and collaborate with your whole company with your data really fast. But what's a tool that a lot of people use? Spark. But Spark's internals don't use Apache Aero, so it's not as fast as it can be. So there's actually 3 projects trying to speed up Spark using Apache Aero. So there's a gluten, okay, that allows you to swap out the internals of Spark, so you can swap it out with like a different engine. Velox from Facebook is one of these engines is a drop-in replacement for Spark. So you would just say, okay, hey, I'm going to just swap this out, and now going forward when I use Spark, it's actually using this Velox guts that use Apache Aero for faster. And then Data Fusion has its own version of this called Data Fusion Comet, where it uses data. We basically are swapping out Spark's internals for Data Fusion. Okay, and so basically, not only is Aero allowing you to create these new, faster tools, but it's also allowing you to take pre-existing tools and make them faster. So Apache Aero is just creating this sort of universal world of just really fast data processing, which is pretty exciting. And everything's kind of being built in lots of little pieces to work kind of around that. Because once you have this like standard way of representing data in memory, you can build other things. Like there's other things that are being built around this, or things like projects like Substrate, where Substrate is a project that's trying to create a universal way to represent query plans. Okay, so to get a little into the weeds, like the way a database or data warehouse engine works is they would take your SQL, they would parse your um, SQL, and it would turn into a relational algebra expression. And that relational algebra expression is really what it ends up becoming in a query plan. So the idea here is Substrate is to create a standard way of expressing relational algebra to create sort of universal query plan. So the idea is that any query engine, if they know how to read the Substrate format, they can reproduce the same query execution plan across different engines. So that's another project, and that's kind of ties into Arrow because it uses sort of Arrow ways of talking. And Apache Parquet, also is really built to kind of really be quickly loaded into Apache Arrow because they've kind of all these open source projects talk to each other. So a lot of these really cool things make it where now you don't necessarily need to have a big integrated data warehouse to have really fast data processing. So that's a key point here. The reason why the data lakehouse is possible is because you have technologies like this that allow you to have fast queries on data anywhere. The system, the storage system, and the compute system don't have to be intricately tied together anymore to be fast. Okay, and that's what makes data lakehouses possible. The other piece of the story is Apache Iceberg. And Apache Iceberg is a table format. So let's kind of break down what a table format is. So when you have a data lake, your data lake is essentially a big pile of files. Okay, so you have like Parquet files, CSV files, JSON files, whatnot, but they're just files. Okay, and that's great. I mean, at the end of the day, it's a storage system which is meant to store files. So that way you can retrieve those files when you want and retrieve them quickly, and so forth. That's all well and good. But when you're working with analytics, what you want are tables. Okay, you don't want to look at 1,000 Parquet files. You want to look at the sales data set, the sales table. So what a table format does, it says, hey, basically the simplest way of looking at it is it's a grouping. It's basically some way of telling a tool like Dremio or Spark or whoever that, hey, these files right here, that's table A. These files here, that's table B. And that way, I no longer have to look at the world as these 9 files. I look at it as table A and table B. Okay, and you have that abstraction that allows me to write SQL and say, hey, select all from table A. So when I say select all from table A, now Dremio knows what I'm talking about because it knows these 9 files are table A. Okay, and it can go and then read those files, load that data up, and go from there. Now, originally when table formats were created, the original table format for like data lakes was Hive. And Hive wasn't trying to create a table format. They were trying to create something else. Because when data lakes first started, it was really started with Hadoop, which came out of Google. And Hadoop, the idea behind Hadoop was to say, hey, you know what? Let's try to use cheaper computers for storing lots of data. Because these data warehouse systems on-prem are really expensive. And you're basically buying a really expensive computers for data you're just storing. So what we'll do is we'll take cheaper computers with really big hard drives, chain them together in one big network, and treat them as one giant hard drive. And that's essentially Hadoop. There's a bunch of other cool niceties and replication and lots of other really good stuff, but that's essentially the idea. And while we have this system, wouldn't it be nice if we could do some analytics on this system? So then something called MapReduce was created. And MapReduce was a framework for writing analytical jobs to run on those Hadoop systems. But MapReduce code had to be written in Java. And most analysts either don't know Java or don't want to write Java. Just to write, where they could write in a simple SQL statement. So there was a demand to write SQL instead of MapReduce. But MapReduce was the framework. So Facebook, if I remember correctly, created Hive. And Hive basically said, you write SQL, we'll take that SQL and we'll turn it, and it'll convert it into the Java MapReduce code. So that way, you just have to write the right SQL, and Hive will do the rest. But in order for that to work, you need a table. Okay, basically Hive has to understand what is a table in order to be able to translate that SQL into MapReduce. So the way Hive did it said, hey, okay, any files within the same folder is a table. So if you have a folder called table A, or directory called table A on your storage, we're going to just treat anything inside of there as table A. And so when you write select all from table A, it really just means select all from whatever the data is from all the files in that folder. Okay, and that worked. That allowed you to write SQL, and the MapReduce jobs would write the right MapReduce code, and you were able to run queries much easier on these Hadoop clusters. That eventually evolves into all sorts of other things, and Hive is still around today, so Hive is kind of no longer just a Hadoop thing. It's now just a general way of cataloging your tables. But that's essentially like the impetus. The problem with this, though, is it wasn't perfect, okay? While Hive became the de facto standard, when you're working with files as a folder, what happens is you're lacking of a context. Hey, what files are in the folder? Like you have to like literally every time you run a query, I have to go look in the folder and then list every file that's in that folder and then read every file in that folder to understand what the data is. That takes a lot of time. Okay, it would be nice to already have some sort of idea what's going to be in that folder ahead of time. Okay, so while Hive definitely enabled the ability to do things like partitioning, which you couldn't do before, allowed all the different files to be used, allowed you to do some level of atomic updates through usually at a partition level. It was an improvement from what came before, for sure. But over time, as people kept doing more and more with Hive, lots of challenges were found. Okay, if you want to do like a small update, like you want to update one row, you find yourself having to rewrite the entire partition just to update one row to update it atomically. Okay, there's no way to make changes to multiple partitions at the same time safely, or make changes to just have multiple changes happening at the same time in general. All that listing of files just took a long time from a computational point of view. So overall, it just meant slower queries. Okay, and then on top of it, like the way partitioning worked required that the analysts have to really understand the table. So it was really easy to make a mistake and have a much slower query. So overall, it wasn't perfect. Okay, and on top of it, like Hive wasn't tracking table statistics, so you would have to manually run these analyze queries periodically in order to get those table statistics to optimize queries, so that way engines can run faster, and that was very cumbersome. Okay, so the idea is that you had all these problems, and Netflix was a company that was using Hive, and they were running into these problems. So they decided, hey, we need to make something better. Okay, and so Netflix is having this problem. Uber's having kind of a similar problem, a little bit more related to streaming, and then Databricks is also trying to figure out the similar problem. So all three of them kind of figure out a solution to this problem, which is how do we represent a better way of representing a table on the data lake. And generally, they all kind of come to a very similar conclusion, and that is the metadata, the thing that tells you what the table is, shouldn't just say, hey, this folder is the table. It should actually tell you which files. It should be a specific list of the files in the table. So now all three of these formats, Apache Iceberg, which came out of Netflix, Apache Hoodie, which came out of Uber, Delta Lake, which came out of Databricks. Basically what happens here is you have files, and it's not based on the folder that the files are in, it's based on the metadata. And basically what happened is that an engine like Dremio would read the metadata, and the metadata would say, hey, these are the files that are in the table, along with other statistics that can be used for optimizing the query. So when we think about a specific table format like Iceberg, what is Iceberg at the end of the day? It's a table format specification. Okay, it's not like a program. It's a standard for how you write metadata. So those files that describe that these files are part of the table, these Parquet files are part of the table, how do those metadata files look like? Iceberg writes a standard. Now, any tool that wants to use that standard can use it. And that's the beauty of it. That's the beauty of standards. Anyone can use it, and now everyone's kind of working from the same playbook, which allows for more interoperability. So Iceberg also, kind of like Arrow created libraries in each language to help people use Arrow, Iceberg creates libraries in many languages to help people use Iceberg in those libraries. Being able to, basically these are libraries that give you functions and tools to write Iceberg metadata and to read Iceberg metadata. But Iceberg is just a way of writing metadata to identify a table. That's all it is. It's not a storage engine. You'd still store in like an S3 or an ADLS or a Minio or a Hadoop. Okay, it's not an execution engine. Okay, you don't execute queries with the Iceberg libraries. You would execute queries with a Dremio. You would execute queries with a Data Fusion. You would execute queries with an Apache Spark. And it's not a service. Okay, it's not this thing that's on all the time. Okay, they're just files on your storage, which is a really nice thing because you can have tables that exist that don't require a database system running 24/7. They just exist in your file storage and they can be read. And that can save you a lot of money when you think about, traditional database data warehouse systems. They kind of have to constantly be running to maintain that accessibility of the data. So the Iceberg format is essentially a structure like this. Okay, and essentially the idea is this is the metadata. So this section right here is the metadata. Here are my Parquet files. But at the top, there's a thing called a catalog. Okay, we're not going to talk too much about catalogs in this presentation, but this would be something like right now there's Nessie, which is an open source catalog, and then there's Apache Polaris, which is an incubating project for the Apache Foundation, which is a open source catalog. But what these catalogs do is that they maintain a list of all your tables. Okay, so the Iceberg format requires that you have one of these catalogs. And basically it says, hey, Dremio or any engine would first go to the catalog and say, hey, catalog, I'm looking for table A. Where's table A? And then the catalog would say, hey, table A is located here. Here's where you find the metadata for table A. And then from there, you can then begin understanding the table. So this first layer, the metadata file, tells me like what's the schema of the table, how's the table's partitioned, what are the different snapshots of the table. And then once I know which snapshot I want to look at, so let's say the newest one, this snapshot will point me to a manifest list. And that manifest list is going to list different manifests. And I know that is like a bit of a tongue twister. But essentially a manifest is a group of data files. So let's say each partition gets its own manifest file listing the files that have data for that partition, that chunk of the table. And then basically the manifest list lists all the chunks that are included in that version of the table. Okay, so basically Dremio would say, okay, hey, where's the table? I'd go here. Okay, I get this, I understand what the schema is. Okay, I'm looking here. These are the chunks I need. These are the chunks I don't need. And then once I identify which chunks I need, I go to those chunks, those manifests, and I start looking at the listing for each individual file and determining, hey, do I need this file? Do I need that file? And at the end, what you do, you create a scan plan, meaning a list of files to scan. And even though the table might be like 100,000 files, really big tables, like it might be 100,000 Parquet files, your particular query may only need 50 of them. And using that metadata, you can walk away only having to scan 50 files instead of having to loop and open up all 100,000 files to figure out what's in them. The metadata allows you to kind of, in a much more compact way, understand what's inside those files. Essentially, it operates like a big index on your data. So not only do you get this ability to define your data as a table, but you get this built-in index with up-to-date stats all the time. So basically, it allows you to kind of scan that data really, really fast. So as I mentioned, the Iceberg allows me to kind of identify where the table metadata is. Then I go to the metadata file, which tells me about the schema and the partitioning. Then I'm going to go to those manifests, the manifest list, which is going to list the different chunks of data that are in there. And then those chunks, which are called manifests, will list the individual data files. And then from each of these files, I can begin reducing the number of files I have to scan. Okay. So this leads to lots of cool benefits. One, that's really unique to Iceberg. Only Iceberg has this feature. It's called partition evolution. In other formats, if you want to change the way you partition your table, you have to rewrite all the data immediately. You essentially have to recreate the table. In Iceberg, you can choose to change the way the table is partitioned, and that will only apply for any data being added to the table going forward, and you can rewrite, if and when you want to, the remaining data. In Iceberg, because Iceberg lists data the way it doesn't require that all the data be in the same folder. This allows you to experiment with different ways of distributing your files or different like physical ways of how you allocate the data on disk to optimize for different storage systems. Because different storage systems have different ways that they work, different guarantees. For example, like on S3, if you have too many files in like the same folder, aka prefix, if too many requests are hitting that folder, it could lead to a reduction in performance. So being able to, if you have a really big partition, being able to split the data files for that partition across multiple folders will allow you to be more performant. Okay, hidden partitioning. This makes it where the analyst doesn't really need to understand the table in depth to really be able to use the partitioning, because the partitioning is actually part of the metadata. So basically, they just have to write their query, and then Iceberg will know based on the metadata whether it can use the partitioning or not, which makes using partitioning and putting a partitioning in place much easier. And that's one of the big things about Iceberg. Iceberg is very much about trying to create that sort of, make that sort of SQL interaction with your data much easier than it was prior to Iceberg. You have a very huge ecosystem. One of the biggest things about Iceberg is that it has a huge ecosystem of tools that can read and write to Iceberg. The thing to keep in mind is not just about reading and writing, it's also about management. And Iceberg is probably the only format that I'm aware of that has a huge ecosystem of tools that'll manage the tables for you too. So Dremio does that, where it can automatically optimize your tables and expire your snapshots, but it's not the only one. There are many other tools and there's many tools and vendors that are offering these management services. While generally with the other table formats, you usually have like one, or for the most part, one choice in each of them as far as who will fill that role for you. Otherwise, you do that maintenance yourself. Apache Iceberg has a really cool open source project, one of those catalogs I mentioned called Nessie, that has a feature called Git for Data, or Data as Code. The idea here is that you can use Git-like semantics at the catalog level to like branch your data. So if you ever used Git, it's like that, where you can create a branch of data so that way you can isolate the changes to your data, or create zero copy clone environments to do experimentation in. A lot of really cool benefits to that. It's a very open project. Like you can participate in anyone can just jump in on the mailing list, the dev mailing list, be in the Slack, whatnot. So you can always kind of know what's kind of going on in the Apache Iceberg world. Pretty easy. Everything's done out in the open in one single public repo, making it again just a very transparent, easy to follow project with a huge amount of contributors from companies like Netflix, Apple, Dremio, and many more. So these aren't you have a lot of companies making sure that this product is alive and well developed. So to kind of summarize, you have these two projects that enable Data Lakehouse. You have Apache Arrow that enables data processing to be fast enough to do more workloads on the data lake. And then you have Apache Iceberg that allows you to take the data we have on the data lake and treat them as SQL-enabled tables in the same way we're used to with a database and a data warehouse. And with these two technologies, it now enables us to really treat our data lake like a data warehouse, aka Data Lakehouse, especially when you have tools like Dremio that help kind of wrap this whole thing up in a nice bow for you. Now, if you want to get hands-on with this, here are a couple different exercises. You can scan these QR codes, and these are hands-on exercises you can do directly on your laptop. So they don't require you to have any kind of cloud infrastructure or pay anything. You can do them 100% for free because everything is spun up on your laptop using Docker. So if you want to do some of these exercises with Iceberg to kind of see how this feels like in practice, these exercises will help you do that. I would start from left to right. I would start with this one, and then these three are the same exercise, just with a different starting database. So you either start with Postgres, start with SQL Server, start with MongoDB, you move the data over to Iceberg, and then you serve up a BI dashboard with Apache Superset. And that's essentially the flow of this exercise. Again, I highly recommend joining the Data Lakehouse Hub community. You can scan the QR code to join the Slack community. I do have channels in there you can join for all the local towns that I travel to fairly frequently to hear about any events there. But feel free to use it as a space to network and talk to other people about cool Data Lakehouse topics. Also, again, I'm traveling all the time, so I also have this Lakehouse this calendar here where you can subscribe to find out about any events that I'm speaking at. This will include virtual events like this one, and this would also include in-person events as well. Whenever, and actually I'll probably do some traveling around the world in the next couple months, so there'll be some international events as well. But you can find all of that there. Again, I highly encourage signing up for all of these things. I will be posting this video up on the Data Lakehouse Hub YouTube channel pretty much as soon as I wrap up here. So do keep an eye out for that. And again, but what I will do is let's see how much time we have left. I think I have time for like one or two questions. So if anyone has a question, let me actually just see if there's a Q&A booth. Okay, that question I answered. If anyone has any other questions, feel free to post them either in the Q&A section or in the chat. I'll give a minute to see if anyone has any questions they would like to submit. Okay. Give it a moment. I Thank you very much. Thank you for the kind words. Okay. Cool, cool, cool. Thanks. But oh, here's a question: does Dremio support other Lakehouse formats? Dremio supports read write with Apache Iceberg, so that's very first class. And the reason, and basically the reason for like that heavy support for Apache Iceberg in Dremio is for a couple different reasons. Like originally, like Dremio used Apache Iceberg to accelerate the way you would work with your data in the data lake transparently. So in a sense, you didn't even know you were using Apache Iceberg when you were using Dremio. So for example, you'd be able to connect to a data lake and highlight a folder of Parquet files and say, hey, I want this folder of Parquet files, and I want to treat that folder as a table. It was referred to as promoting a data set. Okay, and essentially under the hood, what was happening is that Dremio would create like Iceberg metadata around those Parquet files and then Dremio would maintain that Iceberg metadata. And so essentially you were getting the benefits of Iceberg without ever even thinking about Iceberg or knowing what Iceberg is, just by using Dremio to query your data lake. But that required Dremio to manage the metadata and refresh that metadata periodically. Now, as data sets get updated faster and faster and faster, making sure that that metadata is up to date with the minute that those data files change really required that the data needs to be natively worked with an Iceberg. So that was just a natural evolution of the platform, that it has first class support for writing data sets in Iceberg altogether. Because Dremio's query engine is also very optimized to take full advantage of that Iceberg metadata in ways that other engines don't, which is why it has such high performance with Apache Iceberg datasets, and generally with any datasets. Like generally, you can run queries with Dremio against anything, and it's pretty fast. But with Iceberg, it's extra fast. But also Dremio supports Delta Lake tables. It does not, but with Delta Lake tables, it's read only. And then with Hoodie right now, there is no support for Hoodie, but there is a tool called Apache X table in which you can convert tables between formats. So you can convert tables to Apache Iceberg for Dremio to read, which again will allow Dremio to take advantage of its optimizations using that Iceberg metadata. And if you're using something like, let's say you're a Databricks user using Unity Catalog, it does have that uniform feature where you can broadcast Iceberg tables, giving you a route there. So there are ways to get there. But Dremio's engine really leverages the Iceberg format in a way that whether you're using Iceberg or not. So again, if you're using the Dremio platform, you may not even realize that Iceberg is really basically making your life a lot easier underneath the platform in a lot of ways. But also, if you decide to natively build a Lakehouse natively with Iceberg, there's a lot of other benefits that Dremio provides. Also with this acceleration feature called Reflections, where you can create reflections on any data set in Dremio. So it could be a Postgres table, a Snowflake table, whatever. And it works great. It's basically like a materialized view with a bunch of bells and whistles that makes it a lot better, a lot less of a storage footprint, a lot more reusable. Basically a really fantastic acceleration feature. But when the underlying data that you're reflecting or you're using this reflection feature on is an Iceberg table, you get additional benefits where you get incremental updates. So basically when the data set changes, it'll automatically refresh the reflections, but also it can do so incrementally. So the speed at which it can do so is much faster because it's capturing like that change data to only update. Not instead of rewriting the reflection, it only incrementally adds what's been added to the reflection, giving you a much sort of giving you additional value. Again, it's not necessary. Like a lot of people can get plenty of value just using reflections on data sets and just working with Dremio directly querying their data as it is. And again, Dremio has its ways that it's optimizing all of that under the hood that the user never needs to worry about, never needs to think about. But when you do explicitly create an Iceberg data lakehouse, Dremio you get a lot of little extra niceties that are tremendously valuable. Cool. And now, what is the exact difference between Hoodie and Iceberg? I won't get too deep into that one because that I could spend a whole hour on. But basically, all three formats, Hoodie, Iceberg, and Delta, they're just architected differently. So the metadata looks different. The way the metadata is organized is different. If you sign up for that Apache Iceberg crash course, I'll go back to that QR code. So let me go back to the beginning of the presentation. But if you sign up for that Apache Iceberg crash course, the second lesson in that course is literally me just going through the three formats and going through the differences in their architecture. And then again, if you understand where each one comes from, again, Hoodie was there to kind of handle sort of like high speed streaming at Uber, because Uber, you have a lot of data coming in constantly from people doing ride sharing. So here's a course you can sign up for through that QR code. But basically, if you understand that, the Waze design makes a lot more sense. So I recommend watching that. Here I go in a lot more detail about Apache Iceberg across 10 sessions than I can in one session here where I'm going over Arrow and Iceberg. But hopefully you guys enjoyed this session. Again, I'll go post this on YouTube shortly. I'll actually right now. Yeah, keep going. Make sure you've joined the meetup group. There'll be more Lakehouse lunches to come in the coming weeks, and I look forward to seeing you all there. Have a great day.